Hello everyone, welcome to the fourth session of the quantum field theory. Today we are going to talk about the remaining topics from the last session, and after that we are going to discuss the Dirac field. But there were a few topics that we didn't talk about. The first one is the time evolution of the Klein Gordon field, how we expanded the Klein Gordon field based on the momentum, but only we talked about the spatial component of the momentum and the space coordinate, and we postponed talking about the time evolution of the Klein Gordon field. Today we are going to see how to do that, and we are going to talk about causality in Klein Gordon field and how causality is preserved and how the problem of causality can be fixed with the formulation of Klein Gordon field in quantum field theory approach, in contrast with classical quantum mechanics, which the causality was a problem. We already talked about it in the first session. So we are going to talk about these two topics, and this video is probably shorter than the usual videos. But in the next session, we are going to start talking about the Dirac field and the fermionic field, and then we can talk about calculating the cross-section and processes in quantum electrodynamics and more applicable topics. So in the previous session, we talked about Klein Gordon field, but only as a function of a space, which means that if I write phi of x like that, I mean phi of x at time equal to 0. So we are typically talking about a frozen picture of a field in time, but now we're going to see how to calculate phi of x and t from the initial configuration of the field. So we basically have the initial field phi x t equal to 0 at some time, at some snapshot, and then we are going to use the Hamiltonian or the dynamic of the field in order to calculate phi of x at any particular time that we are interested in. So phi of x at t equal to 0, as we previously talked about, is the integration over all possible momentum with proper normalization factor. So a dagger of p, the exponential term, plus a of p I p dot x. But probably the most important part is this red part. So p dot x, we mean only the spatial component of momentum and the coordinate, which means px plus py y plus pz z. And now we're gonna bring the time factor into that, and we are going to show that this p of x, when time comes in, so we're going to show that if we are bringing this time component, we're going to have a 4 vector product, which means it's going to become like p mu x mu, and we only have the 0 component here, and then we have a Lorentzian signature, which is a minus, and then we have p dot x. And we're going to prove that. This is not something that we can just bring it out from our pocket. We need to show that with this snapshot of the Klein Gordon field and then evolution of it with the Hamiltonian, we can get the same thing as we expected from the Lorentzian signature. So we previously talked about Heisenberg picture. So there were two ways of looking at the evolution of quantum mechanical operator: the Schrödinger picture, which you change the state as a function of time, and then we had the Heisenberg picture, we are going to also talk about another picture, which is called interaction picture, but we are only going to talk about it when we have the interaction of the field or perturbative interaction of the field, which is a mixture of these both pictures. But now we're going to talk about the Heisenberg picture. In the quantum field theory, we adopted Heisenberg picture, which the time evolution is attributed to the field time evolution, and the fields are operators. So we're basically going to talk about the evolution of the operator as a function of time. And basically, when we want to calculate phi of x and t at any particular time, this evolution, if I put this operator sign on top of phi, is going to be like this. The phi of x and t at t equal to 0, and this t equal to 0 is any time origin that you want to put. So any time that you specifically know your field configuration at any particular time, you can call it t equal to 0, and then have the evolution of this field throughout these exponential terms. So now let me put all the operator signs on top of each operator. So we are purely dealing with some operator evolution. And this is called Heisenberg picture. And the H or Hamiltonian operator is the total Hamiltonian operator. And by total means I'm not talking about the density of Hamiltonian operator. I'm going to talk about the integration of Hamiltonian all over all space. The total Hamiltonian operator is the integration over a space of some Hamiltonian density. And the Hamiltonian density is calculated with the local field. So h of x, and the Hamiltonian density is simply phi dot of x squared plus the gradient of phi of x squared plus phi squared of x. And if you integrate it, that's a whole Hamiltonian. Now, something simple that comes into mind is what is the commutation relationship between the Hamiltonian density of momentum and each of these A of P or A dagger of P. We need to calculate that, and we're going to see it's going to be useful when we are using the Baker-Campbell-Hausdorff formula. So when I'm basically trying to write down H of P and A of P commutation relationship, I need to calculate the following commutation relationship. So the energy factor, A dagger of P, A of P with A of P plus E of P over 2 I and A of P. And the second term is 0. So good for us. We only have to deal with the first term. So to calculate this term here, we can write it down as A dagger P, AP, AP plus A dagger P, AP, AP. So that's a basic formula when we have the multiplication of two operators trying to commute with the other operators. We can simply use that formula here. So the first term is 0. And the second term here is, so this term here is minus delta of P minus P prime. But since P and P prime are the same, so we can just ignore the delta and just replace it with 1. So this term is going to be minus AP. So HP with AP would result in minus EP AP. So now we have this term. We're going to use that in the evolution of AP. Now let's go back to the main problem. Phi of x and t is equal to phi of x t equal to 0, exponential of IHT, exponential of IHT. And this is going to be, so we keep those terms here, but we can expand this and we have this a dagger of p exponential of p dot x plus a p e I p dot x. So basically, this expression can be written as the integration over all momentum and then these evolutions are sandwiching those a and a dagger. So we're going to have this term a dagger of p sandwich in between IHT times IP dot x plus IHT a of p minus IHT an exponential of IP dot x. Now the question is how to calculate these terms. Terms I and terms 2i. And we're going to use this formula here in order to calculate those terms. So let me call AP as a function of time as basically the evolution of a dagger P and AP of T as follows. Now I'm going to show that this is going to be a dagger of P exponential of IEPT. And this term is going to be AP E minus EPT. So how to prove that? We're going to use this formula, Baker, Campo, Hausdorff formula. And we say when we have AP sandwich between IHT minus IHT, this is going to be AP plus the commutation between H and AP with the proper coefficient IT squared over 2 factorial of the commutation between H and the commutation of between H and AP and so on. So we know this term. This is coming from here. We want to calculate the second term and also find out the pattern of how it evolves for the rest of the higher order terms. So the commutation between the Hamiltonian of AP is equal to, we basically know this term. This term is equal to minus EP of AP. So we just have to calculate H and minus EP and AP, and it would be minus EP out H of AP, and it would be, again, EP squared AP. Now we understand this pattern is just bringing out this energy factor out. So for the next term, it would be minus EP cube AP. So basically, AP sandwiched between minus IHT, IHT can be written as AP minus IT, EP, AP. The next term will be IT squared 2 factorial EP squared AP, and the other term would be IT cube 3 factorial EP cube AP, and so on. So we just basically have the AP, so we can take this AP out, factor it out, and we would lead into I minus IT EPI as IT over 2 factorial of EP squared I. And we just basically can write these terms as exponential of minus I EP T. So AP minus IHT, the evolution of AP with the time can be simply written as AP times exponential of minus I EP T. And for the A dagger of P, the similar logic can be used, but we have a different sign here. So you have A dagger of P exponential of I EP T. Now, it is simple to write phi of x of t as the sum over all momentum, 2 pi over 3, 2 EP. So now the first term turn to A dagger P, evolution exponential of I EP T times exponential of minus IP dot x plus AP, the exponential of minus EP T times exponential of IP dot x. And now we can just simply write it as A dagger P. So this term can be written as exponential of I EPT minus P dot x plus AP exponential of I minus I EPT minus P dot x. And now this whole term can be re-expressed as a dagger of P exponential of I. So this term is basically the 4-vector inner product with the Lorentzian signature. So now everything makes sense right now. Of I, let's say P mu x mu plus AP exponential of minus P nu x nu. And that's how the whole time evolution of the field can be understood from knowing this one snapshot of the field at t equal to 0 and be known as at any particular time. Okay, now we are finished with part 1. We just showed how to rewrite the Klein Gordon field at any particular time, because in the last session we only talked about the space evolution and we left out the time intentionally to just use this technique to calculate at any particular time. Now we are moving into the next session, which is the concept of causality and how the concept of causality can be fixed in quantum field theory. Okay, now let's talk about causality. So for the concept of causality, we need to calculate the expectation value for the phi of x and phi of y. There is two interpretations for that. The first interpretation is the expectation value for the field, or the field value, at 2 points of x and y. The second interpretation is that we create a particle at point x and project to creation at point y. So basically, the first expectation value means that if we have in a space-time, imagine this box is a space-time, and this is point x and this is point y. So imagine we are quantum mechanically studying the value of the field phi, that could be shown as phi of x at 2 different points, and we multiply them, and then the expectation value of this multiplication can indicate the effect of these 2 points on each other. So if this expectation value goes up, that means there is a correlation, anti-correlation, or no correlation between the 2 points. So the expectation value of a correlation function is something that could be seen as the probability of any possible effect between the 2 points. So if something happens at point x, what is going to happen at point y. And the other interpretation is that we create a particle at point x out of vacuum, and then we want to see what's the probability that we can project it to a particle creation at point y. This is called propagator or propagation, which means that on the quantum mechanics scripted language, we create something at point x out of vacuum, and then we want to see if something is going to pop up at point y out of vacuum. And therefore we can understand if any particle which is created at point x propagated into the point y. And we're going to show that this is going to be related to the concept of causality. So we can basically calculate this value simply. So phi of x can be explained by the expansion. You can write it like this. And phi of y can be expanded on p prime. Okay, now let's try to do this calculation. So we don't have to write basically everything down. So we're going to write it down as zero, the vacuum. And then we have the integration over p and p prime. And then two energy factors. But the whole point is that we have this a and a dagger multiply to each other. So we have first this term, a dagger p prime, a dagger p, a p prime, and then we have ap, a dagger p prime, and we have this ap prime. And of course, there are some multiplication coefficient behind them. So I'm not going to write it down, just for the one which is relevant. So now, among all of those terms, only one of them survive, because when we have this vacuum here and when we have this vacuum here, so for example, this term here is going to be 0, because when AP prime acts on the vacuum, that would be 0. The other one is this term, again, because there is annihilation acting on vacuum, that's 0. And when a dagger P acts on vacuum, on the other side, it's also going to be 0. So we are only going to have... Okay, now I can rewrite it as the expectation value. Let me see. Now I have the vacuum, then I have AP, a dagger P prime, and then I have the exponential term I P prime dot y and exponential I P dot x. So I can take these two out also. So I'm going to put them like here. And then I'm going to go to this term. So this term I know, going to be 2 pi 3 delta p minus p prime. We calculated in the previous video. So we're going to have, let me just copy this term here. Just don't write it down every time. And then these two factors here. Oops, sorry. Times 2 pi 3 delta p minus p prime. And now we can do the integration over p or p prime. It's up to us, because p and p prime are arbitrary choices. For example, let's say we are going to take it over p prime, because it's less convenient to write everything as p prime. So we're going to have, so we are just replacing every p prime with p, because we have delta p and p prime. So we're going to have delta 3p 2 pi. So we have 2 pi 3 canceling out with this 2 pi. And then we have 2. And then the energy factor would be EP. And then we have E minus P dot X, an exponential of I P dot Y. And that's it. So this term is going to be written as 2 pi over 3, 2 EP, exponential of minus EP y minus x. Okay, now let's call it d of y minus x. I mean, it's a little bit conventional to choose x or y, but we want it to be like minus IP. So then I'm going to have y minus x, and then I'm going to call it y minus x. So that's it. That's equal to that propagator expectation value. So now I want to show that why this cannot be seen as something that could be related to causality, because in the special case that we are sure there is no causal connection, we're going to see that that term is non-zero. So there are two types of event, space-like and time-like. So space-like is something that the space is so much larger than the delta t, and for the time-like, that's the opposite. So we're always going to have some events at point x1 and x2 and t1 and t2, and we can have some Lorentz transformation. To take it to x prime 1, x prime 2, t1 prime, and t prime 2. If we have a space like, if you have two events and into the space like points of space time, there is no causal connection. I mean, they cannot logically be connected by causality. Like one of them cannot trigger the other one. That means that we can always find the Lorentz transformation that these two events happen simultaneously, which means delta t equal to 0. I mean, imagine I have some delta x and delta t, and then I find the proper Lorentz transformation when delta t prime is 0, and then we're going to have some delta x prime. And for the time like, if the two events, they can have a causal connection. So if there is a possibility that there is a causal connection, there is not a Lorentz transformation that could make those times equal, but we can find a Lorentz transformation that the two events happen in the same location but with a different time sequencing. So I can find a Lorentz transformation when delta x prime is equal to 0, and then I'm going to have some time after these two events, if there is a possibility of the time like, if there is any possibility of the causal connection between the event 1 and event 2. So we're going to see how in the case of a space like, it is going to lead into the non-zero amplitude if we are only using d of y minus x. So d of y minus x is equal to d3 of p 2 pi 3 of 2 ep exponential of I p dot y minus x. So I can just basically write it down as, I e p t minus, let's say, ep delta t minus p dot delta x. And then imagine I'm in a space like events. So in the space like events, I can have delta t equal to 0 and some delta x. So in that scenario, this would turn into so this term is equal to 0, and I'm gonna have I p dot delta x. And this is non-zero by itself if we integrate over all p. And even if you have a cutoff on p, they wouldn't be equal to 0. So that's a problem if you're only using phi x, phi y. To preserve causality, we need to transform from phi x, phi y to the commutator of phi x and phi y. So that would introduce some asymmetric nature that cancel out for this term. So if I write down, instead of phi x and phi y, the commutator of these two, I'm going to have exactly the d minus y minus x minus d x minus y. So the whole point is that if you're using the commutator instead of each of those individual terms, I'm going to end up with some asymmetric term with respect to y minus x if I take it to minus y minus x. Because for the space-like component, we can do that. We can find a continuous Lorentz transformation to just flip the coordinate between the two events. So now I'm going to write it down as, so that's not hard to show that the expression just turned into this. And this is now equal to 0 because that's the odd function of p. And if we integrate it over p, that would be equal to 0. Now for the case of time-like, so we're going to have delta x is equal to 0, and then we're going to have some delta t. So the expression would be exponential of ip delta t minus so that's again it's going to be 2i sine of p squared plus m squared delta t. But this is not like the sine of p delta x. This is the odd function, but this is the even function. So the even function integral is not equal to 0. So that's how we show that for the space-like events, the expectation value of this commutator is equal to 0, and for time-like, the same expectation value is non-zero. And that's how the problem of causality can be solved in Klein Gordon field theory when we are comparing it to regular quantum mechanics. So that's the whole argument for the Klein Gordon field. Now we have the concept of causality solved, and then we are ready to move to the Dirac field. And in the Dirac field, after quantizing the Dirac field and introducing the special algebra for the Dirac field, we can move into the interaction picture and how the Dirac field and the Klein Gordon field can interact, and we have a minimal theory of fermions and bosons interact with each other. So thank you so much for watching that. I also put these notes on the description, on the comments of this video, so you can have access to the PDF of what I'm writing here. So we would have some complete sources here. Thank you so much.